Welcome to this debate on the nature of dark energy. I am physicist Steven Weinberg, serving as the moderator for today's discussion. Thank you, Paolo Cacella, for allowing the presence of so distinguished physicists. Our panelists include some of the greatest minds in physics: Albert Einstein, Stephen Hawking, and Alan Guth. Before we begin, let me briefly explain the theme of our debate. Dark energy is a mysterious substance that makes up about 70% of the universe and is responsible for its accelerated expansion. Despite its importance, very little is known about dark energy and its properties, making it one of the most pressing questions in modern physics. Now, I would like to pass the floor to Einstein. Professor Einstein, what is your perspective on dark energy and its role in the cosmos?
Thank you, Professor Weinberg. Dark energy is a fascinating topic, and one that has puzzled me for many years. In my theory of general relativity, I introduced the concept of the cosmological constant as a way to explain the static nature of the universe. However, subsequent observations have shown that the universe is not static, but rather expanding at an accelerating rate. I believe that dark energy can be explained by the presence of this cosmological constant in the equations of general relativity. This constant represents a form of energy inherent to empty space itself, and its effects on the large-scale structure of the universe can account for the observed accelerated expansion. However, I must admit that I am still puzzled by the nature of dark energy and its relationship to the cosmological constant. The value of the cosmological constant predicted by quantum field theory is many orders of magnitude larger than what we observe in the universe, which remains one of the greatest mysteries in physics.
Thank you, Professor Einstein, for sharing your thoughts on this matter. I must say that I am in agreement with your view that the cosmological constant provides a plausible explanation for dark energy. The observed accelerated expansion of the universe is indeed consistent with the predictions made by general relativity when the cosmological constant is taken into account. However, like you, I am also puzzled by the discrepancy between the value predicted by quantum field theory and what we observe in the universe. This is indeed one of the greatest mysteries in physics, and it highlights our limited understanding of the fundamental nature of dark energy. In my own work on this subject, I have explored the possibility that dark energy may be a manifestation of vacuum fluctuations in the quantum field theory of matter and energy. According to this view, dark energy would arise from the zero-point energy of all the fields in the universe, including the Higgs field, which is responsible for giving mass to elementary particles.
Thank you both for your insights on this fascinating topic. I agree with both Einstein and Hawking that the cosmological constant provides a plausible explanation for dark energy and the observed accelerated expansion of the universe. However, as you both mentioned, the discrepancy between the predicted value of the cosmological constant from quantum field theory and what we observe in the universe is indeed puzzling and highlights our limited understanding of the fundamental nature of dark energy. In my own work on this subject, I have explored the possibility that the early universe underwent a period of exponential expansion known as inflation. During this period, the universe would have been filled with a dense soup of virtual particles and antiparticles, which would have contributed to the vacuum energy density. This idea is supported by observations of the cosmic microwave background radiation, which show an almost perfect uniformity in the distribution of matter and energy on large scales, consistent with the predictions of inflationary theory.
Thank you, Alan Guth, for your valuable insights into the early universe and the role of inflation in shaping the large-scale structure of the cosmos. One question that arises from this discussion is, what is the relationship between dark energy and the other forms of matter and energy in the universe? Specifically, how does dark energy affect the dynamics of galaxy formation and the growth of large-scale structures such as clusters and superclusters? These are important questions that have implications for our understanding of the history and fate of the universe.